Hello, and welcome to this video on fillet welds. To begin with, let me start by sharing the screen. Actually, I'm going to unzoom, reduce the size of the zoom screen so you can see the PowerPoint that I'm going to share. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. And additional videos on welding can be found on my YouTube channel at Weld Nugget. Today, we're going to look at the subject of fillet welds. I have in the past shared a few videos related to fillet welding, but discussing some details about that aspect. In this video, we're going to look at a broader overview on fillet welds. So what is a fillet? A fillet in a machined component is a profile at the junction of two surfaces which produces a smooth transition. You can see the schematic on the left, and you can see a smooth transition by machining a suitable fillet at the junction of these two planes. On the other edge, there is no fillet. And in this case, if there is fatigue stress at this junction, then there is a likelihood of crack growth from this sharp edge. When it comes to welds, a fillet is a profile that is produced on the outer edge of the weld. And in this case, it also happens in case for solders and brace joints, where you can see a solder fillet. In fact, when we look at solder and brace connections, we often look for that fillet as some measure of quality of that joint. On the right, we can see a cross-section of a fillet weld, where we can see the fillet which has been deposited by adding wire in this particular case. And the dark colored zone is the material which actually melted during the weld and formed that fillet. When it comes to engineering, the word fillet is pronounced as fillet, as in ET is pronounced. The same word is often used in describing a cut of meat, and in that case, it is pronounced as fillet, whereas in engineering, this is pronounced as fillet. Let's look at a single pass fillet weld, how it is made and what it looks like from the outside. On the left-hand side, I'm showing you a screen capture of a video, which I'm going to show you in a minute, made with automated GMAW welding process, so automated MIG welding process. Here we can see the nozzle, which is at the tip of the robot, and you can see the wire coming out over here. And if this was a live action weld, you would have seen an arc form at the tip of this wire. What happens is the arc is very strong, so when you look at it, you have to put it through a lot of filters, and sometimes it's not so clear exactly what is going on. So in this case, I have taken the video without the welding, so you can actually see the movement and progress of the weld during this sequence. So here I'm going to start the video, and let's see what it looks like. I'm going to mute that so you don't get the background noise. Here we can see that the automated gun has come in. It has made a weld. At the end, it retracts. So I'm going to play this again so you can see a bit more clearly this time. And I might pause it a few times on this one. So here we can see that the gun has approached the starting point of the weld. The wire is extended. Again, if this were a live actual welding video, you would have seen a very intense arc over here. And the arc is hot enough to melt a little bit of both the base metals as well as the wire, and it forms the fillet. It starts from the starting point, then it traverses along the length of the component, and then it retracts. In this particular case, in order to make a slightly wider weld, I had chosen to add a weave profile. So you can see that the wire, as long as the gun, as it is moving, it is also producing a little bit of a weave, and you can see that. You can see the weaving motion, and at the end, the weld will terminate, and the gun will go back, and there should have been a weld over there. A weld made under similar circumstances is shown on the right-hand side. This is not exactly the same components, but made under similar circumstances, and you can see a single-pass fillet weld from start to finish. In this case, we are talking about GMAW, gas metal arc welding process, which feeds the wire into the fillet. So you are actually adding wire to create that fillet. In real life, we come across fillet welds in many applications. In fact, fillet welds are probably 80% of all the welds that are made out there. So fillet weld is the most common welding application all over the world in all aspects. Of course, it is more common in structural welds, and you can see a lot of that in car body parts. A lot of the car body parts are made by fillet welding, and you can see a fillet weld over here in automotive steel application. You can also see a fillet weld as part of a railing. So anytime you see a structure, if you are out and about, this actually is a structure in uh, a post office near my house. But if you go to the park, or you go to a library or a bus stop or a railway station or an airport, and if you see any structural forms made of steel, it is very likely that majority of the welds over there are fillet welds. Of the fillet welds, majority are made by MIG welding process because it is more suitable, because you do not need to have very deep fusion, as we'll talk about that later. There are other processes where we can make fillet welds, and those include gas tungsten arc welding or TIG welding, laser welding, and electron beam welding. We can look at these welds and get some idea about the quality by looking at the size, shape, profile, visual defects, and so on. However, to get a full understanding of these welds, we need to look at them on the inside. Now, there are some non-destructive techniques that can be used to look at the welding quality without cutting up the weld, such as ultrasound and X-rays and CT scans. But ultimately, you do need to make the cross sections because that kind of information is not available by any of these other non-destructive techniques. So we're going to see how we cut up these welds and look on the inside. So this is the process for metallurgical sections of welds. On the left-hand side, I'm showing you a component which has two fillet welds. You can't see on the other side. There's a fillet weld on one side and the corresponding fillet on the other side. And I wanted the lab to cross-section it at this location, so I marked it up with a marker, send it to the lab. The lab proceeds by making a cut right along this line with a bandsaw. However, the cutting process with the bandsaw produces a very rough cut, and we don't see a lot of good information from that cut. So then the lab proceeds to mount the sample in an epoxy mount, polish it, etch it. Etching is a process of treating the polished surface with a suitable chemical, which brings out the character of these welds by producing a contrast. And then the lab will take a photograph and email it back to you, and this is what you're going to see. In this case over here, we can see that there are two components which have been welded. There are two fillet welds, one on either side, and we can see the volume of metal which actually melted during the welding process has a different contrast than the volume of metal which did not melt. So the ones which did not melt are lighter gray in appearance over here, and the darker gray ones are those which melted. Again, these contrasts can be different depending on the metallurgy. In this video, we are going to focus more on the size and shape of the fillet welds. We can glean a lot of information about the defects, grain structure, hardness, and elemental distribution of fillet welds from these cross sections, but we're going to save that for a later video. Let's look at a fillet weld in a T-joint. Here we can see an actual cross section of a fillet weld. And it's a T-joint because the two components are coming to form a T. Again, T-joints are one of the most common in the fillet weld design. We have component A and component B. This is again common nomenclature in the welding business. And A has a certain width, B has a certain width over here, And we can see that the contrast of the weld, I'm tracing the arrow tip on the weld itself, and you can see that the weld is pretty large. We can also see that the shortest point of connection from the inner edge of the weld to the outer edge, which is the throat of the weld, is shown by this arrow segment over here. I've drawn the similar weld on the left in a schematic form. We have component A and B, and what we're looking at, leg A. Leg A is the length of the weld in component A, and leg B is the length of the fusion in component B. Now, there are ways to correctly measure these things, and that is covered in another video that I've already presented on the YouTube channel. In addition to the leg A and B, one interesting aspect that comes up frequently in the discussions on fillet weld is the theoretical root and its fusion. So theoretical root is the point where the front face or front line, in this case, because it is a cross section, we can see a line. In reality, it's a plane. The front line of that component A and the front top line of the component B, they come in contact, or at least they meet in a virtual space over here if there's a gap. And that is the theoretical root. Typical fillet welds includes root fusion. So when you say we have made a fillet weld, typically one would expect that the theoretical root has been fused. What that means is the fusion in the fillet weld has extended beyond, at least up to the theoretical root and a little bit beyond. And that beyond along the weld interface is measured as the penetration depth. So the distance from the theoretical root to the actual root is the penetration depth. Oftentimes, the material that you add for welding is quite similar to material that we are welding to. So A and B and the filler wire will be close match, not exactly. And again, there's a separate video on that as well. And let's say that's a close match. So in this case now, we will notice that A is fairly narrow, B is narrow, but the throat is actually much wider. So what that means in this case, that the weld is in all likelihood will be much stronger than the components A and B. So what that means is if you take this weld and try to bend it out of shape, it is quite likely that the components A and B will bend before the weld comes apart. Now, this selection of this size and shape is at the discretion of the welding engineer or the design engineer. The design engineer has to do the analysis and say how big that weld needs to be. And that is an important discussion to have because there are situations where you may want the weld to fail first, and there are situations where you may want the weld to not fail. Now, that again depends on an application and your expectations of the ability to repair. So keep that in mind. So make sure that the design engineer and you are on the same page in terms of what exactly is expected. So this is a very typical cross-section of a fillet weld. We are seeing the theoretical root has been fused, and there's a decent amount of leg on both sides that will give you a required amount of throat. But the fusion of theoretical root is not so simple. Here I'm showing you a cross-section where the theoretical root has not been fused. We can see the fillet weld. We can see leg A and leg B, but there is no fusion at the theoretical root. And I'm showing you the same on the left in a schematic form where the theoretical root is not fused. Now, this is a common misconception in fusion welding that it is a must to have theoretical root fusion. But what you'll find is not all specs require fusion at the theoretical root. So the specs will often say that we need leg A of a certain size, leg B of a certain size, and the external profile of a certain shape, and that will give you effectively the correct amount of throat. But it does not necessary that the root is also fused. In fact, AWSD 8.8, which is automotive arc welding for steels, does not explicitly require root fusion as long as the other metrics are met. So as long as we have the right leg sizes and uh, leg lengths and the outer profile, we will get a theoretical, an actual throat, which should meet the design intent. So that is I'm bringing this up because this is a very, very common uh, source of confusion and discussions in terms of how to gauge the quality of the weld. So make sure you are very clear on what kind of spec that you're trying to meet and what is the expectation from the weld. So this is a typical fillet weld where we get some fusion beyond the theoretical root. This is a weld where we do not get any fusion at the theoretical root. And the other extreme is a full penetration weld. A full penetration weld is a weld where the fusion has gone all the way along the weld interface. Here again, I'm showing you a schematic on the left. It's again a T-junction. And I'm showing you a weld, a cross-section on the right, where given the fact that the base metals are quite thin, with the right welding conditions, you can make a weld which is deep enough that you are actually getting penetration all the way along the weld interface. So that is called a full penetration weld. So the full penetration weld essentially along the weld interface essentially is a groove weld. And the external weld is a fillet weld. So essentially we have made two welds in one pass. So we have made a groove weld and a fillet weld all in one pass. So this is also possible, again, if the components are thin enough and you have set the right welding conditions, you can get a full penetration weld. And this is true when parts are fairly thin. If the parts are less than 4 millimeters, especially in steel, it is not difficult to get the settings to get to this point. However, there are situations where the parts are much thicker and making a full penetration weld as the one I have shown you on the previous slide is not practical. So here I'm showing you a cross section of, again, a T-junction where we have two fillet welds, one on either side. Now, usually, when you use GMAW process, gas metal arc welding process, it is quite common that the largest leg that you can expect from the process and still get good fusion along the legs is 6 millimeters. Now, if the leg length on A and B is 6 millimeters and there's a neutral plane on the outside, you can do the math and you find out that the throat is about 4 millimeters. So if this throat is 4 millimeters and the width of this component is much more, then obviously this weld becomes a weak point in comparison to this width, or this width for that matter. So now if the design engineer wants to make a weld which is as strong or perhaps stronger than the base materials, then the design engineer may have to specify two welds, one fillet on one side, on the other side, but that still gives us about 8 millimeters. So 4 millimeters of throat here, 4 over here, that's 8 millimeters. And if you're talking about shear failure, and if the base metal itself is more than 8, then again, the welds will be the weak point. If you want welds to be stronger than the base material, then the design engineer may have to specify a larger leg length, and that can only be achieved by multiple passes, as I've shown in the schematic over here. So if you want a larger fillet weld, either on one side or both sides, then you have to run this in multiple passes. As I've shown over here, you'll run the first pass, and then you might add another pass and the other one on the other slightly higher. So these additional passes are staggered so that they effectively create a triangle with a longer leg length. So that can be done too. Multipass welds or double welds, and that produces an option. Again, of course, you have to have access to the other side, which is often not the case. So if you have access, you can have these other options for a larger weld. So far, I have shown you fillet welds in T-joints, but there are fillet welds in other designs as well, including lap joints. So this is a lap joint. That means the two parts are sitting on top of each other. and there's a fillet on one edge, you can make a fillet again on the other side to make a dual pass fillet weld. You can do the same for corner welds. In corner welds, the two parts come together with a corner, and you can make a fillet weld on the outside. You can also make a fillet weld on the inside. So these are also very common designs, though perhaps not as common as the T-joints. So in summary, fillet welds account for 80% of all the welds. So it is very important. It's essential if you're in the welding business to understand fillet weldings and all the nuances because they are so common. Of these 80%, majority of them are made by gas metal arc welding process because that is one of the easiest ways to make a fillet weld. In fillet weld, the weld metal forms a fillet on the outside of the metal junction. So the expectation is that majority of that fusion and welding is on the outside, so not a lot along this weld interface. So majority of the weld is going to be outside in most cases. As obviously, it's not always the case. I have shown you some examples over here. So this is the expectation that usually the expectation is for the fillet weld to produce root fusion. That also we discussed. Usually a default expectation is that the theoretical root will be fused. But again, keep in mind that make sure you carefully read the specification you're trying to meet because it may not be necessary or required in that particular case. On the other extreme, we can have a fillet weld which actually produces a full penetration weld. If the wall thickness is thin enough, you can make a weld in a single pass, which can produce a groove weld as well as a fillet weld to produce a full penetration joint in a thin walled section. I need a... If you want to make welds to be stronger, then you can actually make multiple pass fillet welds, as I've shown in the schematic over here. This is a 2-pass fillet weld, so 1 pass on either side, but you can make the leg length even longer by adding multiple passes on top as well. And even though most of the pictures that I've shown you are on T-joints because those are the most common, fillet welds can also be made on lap joints and corner joints in addition to T-joints. As I mentioned earlier, that I have posted other videos which are relevant for this discussion. So if you're interested in finding out more about fillet welding, I would recommend that you watch these videos, the fillet weld measurements, how to accurately measure the fillet weld size and shape, get a better understanding of how fillet welds fail when they are loaded in longitudinal as well as transverse loading. We can understand the effect of arc welding process on weld strength, how the arc welding process itself changes the weld strength of the wire that you're feeding into it. And there's a video on gas metal arc welding spray transfer process parameters to understand how such welds can be made with minimal spatter. Couple of other videos which might be of interest is types of joints and welds, which cover the topic of fillet welds, and introduction to welding symbols, which also covers the topic of fillet welds. I want to thank you for your time in viewing this video. If you're interested in learning more about welding and joining, please do subscribe to this YouTube channel by clicking on the subscribe button below. There are many other videos on this YouTube channel in different playlists, including arc welding, which covers most of this topic, laser welding, resistance welding, and other welding processes, arc design, and metallurgy. So if you want to understand more about welding, please do subscribe and watch these videos. And I want to wish you the very best for your efforts to learn welding, and also wishing you the very best for the upcoming year of 2025. Take care and good luck. Thank you.